I'm absolutely super pleased to be here and to share and then also get some questions and feedback and engage in this sort of international science sharing, which is just so much fun and the of revelation in the Zoom era. Um, anyway, I've been letting this animation play for a little bit, and as Yue mentioned, we're going to talk about canyon overtopping and the connection between sedimentary processes and the record left behind and how it might tell us something about climate, even if it's a little oblique. But I want to motivate first. There's a couple different reasons to study the kind of thing that I'm going to talk about today. Um, and first of all, the one of them is that we're going to talk a lot about Mars and we're going to talk a lot about Earth as well to motivate it too. And so I want to acknowledge my co-authors here. I did a lot of this work when I was at the University of Minnesota working with Andy Wickert, who's there in the Earth Science Department. And I've been collaborating and also getting a lot of great advice from Tim Gouge and Caleb Fassett, who both are experts in the Mars side of these things. So that's less my expertise, and I'll be digging into that more. But so let's motivate it a little bit first with some sort of a more human connection here on Earth. So this is a map of the United States where each of these orange dots is a dam that is monitored and inventoried by the U.S. Army Corps of Engineers. So what this means is that these dams are more than 7 meters high. That is to say, they're pretty big pieces of flood control and irrigation infrastructure. So each one of these dams is a major piece of infrastructure that's monitored and inventoried on a regular basis by the U.S. Army Corps of Engineers. There are 91,720 such dams in the United States of America. That is a lot of large infrastructure, and this does not count. I just want to be very clear here. All of the much smaller dams that are built on farms, built on for small scale flood irrigation control infrastructure. There are, this is a tiny fraction of the actual impoundments that exist in the United States of America for rivers and streams. 17% of these are what are considered high hazard. That is to say, they are um, if they were to fail, they pose a significant risk to the communities downstream in a catastrophic failure. And 2% of those are both high hazard and deficient in terms of their ability to, or in terms of their upkeep and infrastructure maintenance. So that's about 2,300 dams. And here's another quirk that maybe not be true in other places in the world. And so I'd be interested to hear about this. But in the United States, 56% of these dams on this map are actually privately owned. And we'll talk a little bit more about that in a second. So first, let's zoom in onto here, the state of Michigan. So right there in the middle of the Great Lakes region. In 2020, there is this is the Edenville Dam. So this exists sort of in the middle of the thumb there of Michigan. This is a piece of flood control infrastructure and reservoir management that was built quite a long time ago. You can see here it's a pretty typical earthen dam holding back actually two different forks of a river. So it's got sort of two limbs of the lake here. And you can see it's used substantially for infrastructure or for recreation. The dam construction was started in 1923, so more than 100 years ago now. And back in those days, this work was all done by horsepower. And also, there's this innovative new piece of infrastructure called a steam shovel that you can see. Maybe if I use a laser pointer here, you can see this is the steam shovel they had. That was an innovative piece of infrastructure to use at the time. And so this dam was basically built by a group of people from Canada who had their main expertise was actually in running carnivals. But then they decided to get into hydropower, and they came down here and got some financing to build this dam in 1923. And then the main way that the embankment was completed was that a rail bridge was built across the valley, and then tractors would compact the soil. And what you would do is you would fill up rail cars with sediment and soil, drive them over top of the valley, and then just open the sides and empty them into the valley floor. And so that the sediment would accumulate at the angle of repose and form an embankment in this fashion. So there's not a lot of careful engineering going on in the construction of these dams necessarily at the turn of the 20th century. Let's skip forward to about 2018. So in 2018, most dams of this size have to operate using a federal license from the US federal government. And to do so, they need to certify that they're complying with a variety of engineering constraints set by law. And this dam lost its federal license to operate as a hydropower infrastructure in 2018 because of outdated and unsafe spillways. So that is to say, their emergency management system for overtopping events was not adequate. So then because the dam has lost its federal license, it passes under state governance. And so that means the state of Michigan is now responsible for managing or is responsible for governing how and when this dam is operated. And the state has a couple of interests that it needs to balance. One of them being to maintain water levels in the dam for example, endangered species that make that lake its habitat, but then also the competing need for safety. And so this dam came under state jurisdiction, and the operators of the dam had been keeping the water levels low because of safety concerns for the stability of the dam. But then the state sued to raise those water levels to protect an endangered mussel habitat. So there's a lot of competing interests going on here. But 3 weeks after those water levels were raised, a more than 100-year flood, 8 inches of rain fell on central and western Michigan. And I'm just going to play this video to show you the results of what happened at that dam during this large rain event. So you can see that the dam so part of the soil body of the dam actually liquefies. And what's quite interesting is if we restart the video in a second, you'll see a couple of interesting things happen, but it liquefies and slumps in a landslide fashion, and then water starts to rush through the gap, and thus enlarging the hole in a positive feedback process. So I'll play that one more time, and I want to draw your attention. If you look at the landslide material as it moves away from the reservoir, you actually see pressurized water spurting out of the soil matrix. So there's actually overpressure, and that's part of what's weakening the structural integrity of the dam here. So again, I'll recall, like, here's this dam was actually built using this really old technique with a lot of sort of with sort of just like dumping material out basically to build an embankment. And what's interesting is that after the dam actually failed and the lake drained, it turns out that they actually found the old steam shovel. It was under the bottom of the lake. And I'll highlight that this dam was actually privately owned. So part of the reason for the mismanagement and underinvestment in this critical flood control infrastructure was because it was privately owned, and there's not a lot of incentives to keep that kind of infrastructure up to date. Moreover, it's interesting that the failure of this dam produced such a large flood that propagated downstream to the next reservoir in the line along the river that dam also failed. And then the entire city of Midland, Michigan, which is home to several chemical companies, was flooded in several feet of water and had to be evacuated. So this major emergency was precipitated in no small part because of the difficulties of administering flood control infrastructure in the United States. Anyway, I didn't do a lot of this background research. This is not, I was, at IU when I learned about this. And so most of this work was done by an incredible postdoc now a postdoc at Caltech, but a PhD student at Indiana University named Harrison Martin. They just published this research recently, and they did so much more, and I will not talk about it here, but they did so much more on this dam failure, they actually have before and after LiDAR from this dam failure, and you can measure the geomorphic change that happens after this catastrophic dam failure and its impacts on soil and the environment. So I really encourage you all to go and read this. It's quite a cool paper. A lot of interesting science going on here, and Harrison's really took the lead on all of it. So I'm thanking him for all of the pictures and background information that he provided for me on this. So the outcome of this, right, is that this dam failure, and you can see here a picture of the Edenville Dam in the middle of the biggest part of the flood as the lake is draining. Um, and the sort of takeaway here is that dam failure can be catastrophic, but it's also imminently preventable. Outburst floods from natural and artificial dams are a really big deal. They can happen all over the place, and there's a lot of processes that can impound water on planetary surfaces. So not just artificial dams, but also things like glacial glacial ice dams, moraine dams, and any number of different processes can present a barrier to water, allow it to accumulate, and then fail catastrophically. And so what you can see here is that what we actually have left behind is we continue to have a part of the dam, a remnant remaining. And then there's a geomorphic piece of evidence left behind here showing how this catastrophic change happened. But it's perishable and it's going to get reworked over time as this river continues to flow. So I would propose that the best way or the better way to predict consequences for dam failure has to draw from both these artificial examples where we have catastrophic artificial dam failures in here and elsewhere, but also look to natural examples. But the thing is, unlike this example here in the Edenville and Sanford dams, where one has the ability to go and find archival LiDAR before the flood, and then take and acquire new LiDAR and gather new data after the flood to compare before and after, most of the time we only have the forensic record, that is to say, the post hoc landscape change. We don't have the change that happens before, or the state of the landscape before. And so the final shape of the landscape here in Edenville and Sanford, and in any other outburst flood environment, is sensitive to the initial conditions, but it's also sensitive to being reworked by subsequent erosion and deposition. And so on Earth, that's really problematic because rain continues to fall, water continues to flow, and the surface will become eventually reshaped entirely through both tectonics and surface processes. But outburst floods are also, and dams, this problem is also actually turns out to be a very useful tool and an important tool for understanding Mars's paleoclimate. I'll walk you through an example of how that works. Let's zoom in here on a crater on Mars. So you're looking at a terrain hill-shaded image of a crater on Mars. And in this crater, we can note a couple different things. Here's the sort of outline of the crater rim. And on this crater rim, you can trace around the perimeter and you eventually find that this is actually not a closed basin. That is to say, it's not a pool. It's actually a hydrologically open basin. So what do I mean by that? Well, you can see here there's a canyon. I'll just flick back and forth a couple of times, but there's a canyon that actually flows into this crater. So water at some point in Mars's past accumulated, pooled, and then ran through the crater rim and into the basin. But there's also an outlet canyon. So I'll flick back and forth a couple times. This canyon slopes away from the basin or from the crater and can convey water out of the canyon, out of the river, out of the crater and elsewhere onto the surface. And so what this implies is that at some point in this area's history, there was at least enough water to trigger an outburst flood that overtopped the crater rim, carved this canyon, and then allowed all of that water to escape elsewhere onto the surface. However, there's at least one, but there might have been more than one. And so we don't know how much, to the extent of this shape of this canyon, was determined by the initial conditions, that is the first flood that formed it, versus the subsequent floods that may have occurred or continuing water flow if Mars had continued to be wet for a long period of time and supported sustained precipitation on the surface. So here we have a kind of a basic tool. And so I'm going to show you a topographic profile along this canyon. So this is along the outlet canyon that leaves the crater. And you can see that there's actually a remnant of the rim that remains. So there was an initial crater rim that formed, and then the canyon here is actually still retains some portion of that crater rim. It's still the profile from the center of the crater out to the canyon is first goes up in topography and then decreases in topography. So there's a rim in the middle. And if we take a set of profiles adjacent to the canyon, but across the crater rim, we sort of take an average of them and we can get an estimate or an approximation of what the crater rim might have looked like prior to the outburst flood that formed the canyon. So you can see here that a substantial amount of rock has been removed and moved downstream by the flowing water, but that it wasn't able to completely erode away all of the possible sediment that it could have. So we're going to measure a couple different things, and I'm going to pose that this is evidence of we can use this as evidence to better understand how often and when water may have flowed across this canyon floor. So we can quantify a couple different things. We can quantify the slope of the canyon. We can also measure based on the rim of the crater and the lowest elevation present along the uneroded rim of the crater. We can estimate the amount of water that may have been held in the crater prior to the outburst flood. And then we can also measure and approximate the volume of the dam, or that is the rock that was holding back that water. So we're going to do this across a couple different craters on Mars, and it turns out that outburst floods are actually a major process shaping the early wet surface of Mars in the Noachian Hesperian. And so these craters here, I'm showing you a small sample of them, but they're a data set of open basin craters that was collected by my colleague Tim Gouge and published in Geology in 2019. And so these craters were all evaluated individually and shown to be sort of hydrologically open. And so what we're going to do is we're going to try to investigate to what extent do those crater lakes and their dams tell us something about the frequency and magnitude of water flow across the surface. So I'm going to plot them up here in a kind of a non-dimensional space, and I'll walk you through what I'm showing you here in this plot. So the first thing to note is that crater lakes and their dams vary very widely in size. So some craters are huge, some craters are small. And so we're gonna look at the impact of that on basically the final slope or the current state of the topography. So on the y-axis here, we have the final slope, that is to say the shape of the canyon now, as it currently is measured. And you can see that the slope of the bottom of these canyons that exit these open basin craters varies over by about 2 orders of magnitude, so quite a lot. And on the x-axis, what I'm showing here is a non-dimensional or a ratio between the volume of water retained in the basin and the volume of rock that was holding back the flood. So what we have here is an initial size ratio, you may call it, where if a bigger lake has a smaller dam, we can have it would plot sort of high on this, it would plot large on this x-axis, and then if it were the opposite, it'd be a there. So you can also see that the Martian lakes, these crater lakes, vary in size relative to their dams by over 3 orders of magnitude. And so I'm just going to plot up all of the data here. So these are those basins from across that I showed you on the map on Mars, and you can see that there's a couple different trends that pop out in this non-dimensional space. First is that in general, the slope of the canyon, that is to say the final slope, the slope today, decreases as a function of the initial size ratio between the lake and the rim, the lake and the dam. But there's quite a lot of scatter, particularly at these small lakes with large dams. So relative to the size. And so what I'm gonna do is I think I'm gonna try to explain some of this variability with a very simple physical model. So right here I'm showing you an animation. I'll show you a set of animations, and what I'm going to show you is basically a zero-dimensional model. So there's no spatial component here. We're going to model a crater rim as a triangle, as a triangle volume of sediment holding back a rectangular lake. And so in this way, we're going to capture the essential ingredients of overtopping of a dam, like that video I showed you from Edenville and Sanford. But we're not going to have a landsliding process, but we're going to have that overtopping process encoded in here. So as water flows over the top of the dam, the first reaction or the first product of that is to erode sediment from the crest of the dam and distribute it towards the toe. And so this wedge of sediment is going to evolve according to a sediment transport relation, which moves sediment from the top of the dam to the bottom of the dam, thus lowering the slope. And so as flow erodes the dam crest, this of course opens the aperture that water can flow through. And this increases the erosion and increases the discharge, which is a positive feedback. So we have a positive feedback process going on here. And then as the flow erodes material and moves it towards the toe, this of course decreases the slope, which decreases the effective discharge or the available discharge that one can move through the system, which then decreases the erosion and then creates a negative feedback process. So we have two competing feedbacks. And so what happens when we encode both of those into a simple model, what we basically can do is a very, very cartoonish version of a dam overtopping where water flows over the top, initially begins a runaway process of erosion, and then eventually the process self-arrests due to that negative feedback process I was talking about. Okay, so if we run this model many times with a variety of different input conditions, we can systematically vary, for example, the ratio of the size of the lake to the dam, and then we can measure what the final slope of the experiment is in the numerical model after the fact. And that's what this curve represents right here. So for example, this point on the curve would represent a dam with a small lake relative to the size of the dam. And so the outcome is that the slope, the final slope is high. Whereas if we have a very large lake and a small dam, then the slope tends to be small after this process has self-arrested. And so you can see that at work here, and I'll just show you two cartoonishly different examples here. But in one of them, when we have a small lake relative to the size of the dam, the negative feedbacks win out, and the slope effectively remains unchanged from the initial condition. However, when the size of the lake is really large relative to the dam, those positive feedbacks went out, and the final slope will actually scale systematically with the size of the lake, which is what we showed in that plot. So let's throw that basic model up here we were kind of looking at before, and that explains some of this systematic trend. That is to say, larger lakes should produce lower sloping canyons on average because the outburst flood is sustained for a long period of time. However, a substantial amount of scatter remains. And so what else might be a controlling factor? Well, I told you before that we measured profiles across the canyon rims, and what we were able to sort of see as this process is it turns out that not only does the size ratio of the dam to the lake vary by a lot, but so does the aspect ratio. So some craters have just absolutely gigantic, wide, low sloping crater rims, no matter how you measure their profile along the outburst flood canyon. So, and for example, and then some of them, however, are sharp and pointy. So if we look here, we can look at this is all of the examples from our study, and I'm just showing you at the same vertical exaggeration that this aspect ratio, you might call it the length to the width, or the aspect ratio of the dams in profile, varies also by about 2 orders of magnitude, so quite a lot. As again, it's a non-dimensional number. And so now I'm going to plot those points again, but color them by the aspect ratio. So the color bar here on the right-hand side varies from dark, meaning small initial aspect ratio, the aspect ratio of the crater rim, to those pale hot colors, which are indicating very high aspect ratios, that is to say, high length width. So I can demonstrate this for you so that it's a little bit more evident. This point right here is a dam from I think the southern portion of Mars, but it has a very low aspect ratio. That is to say, it is sharp and pointy. Whereas this one that's more intermediate in aspect ratio is something more like a triangle. Whereas this one that we have at the bottom, again, these are all shown at the same vertical exaggeration scale, is wide and broad. So now if we add that as a component into our model, then we can vary the initial shape of the crater over top, the dam that's overtopped. We can see that this aspect ratio of the dam systematically changes how the initial size ratio results in a change in the downstream slope of that outburst flood canyon. So for example, here we have again that small lake with a small dam. And again, these negative feedback processes went out. And so the initial slope, that is to say, the initial slope remains essentially unchanged after the outburst flood because those negative feedbacks went out. The same thing is true for a lake with the same size ratio, but where, for example, the dam itself is wide and broad. So in this wide and broad dam, you can actually sustain a larger lake, and you can those negative feedbacks win out for a larger range of lake sizes. So even this very large lake here, relative to the size of the dam, has difficulty producing a runaway flood because that dam is just low and broad and difficult to erode. So those negative feedbacks went out. Okay, so wide, low-sloping dams are less prone to outburst floods. However, even when you have long and broad dams, if you have a sufficiently large lake, you can still produce a catastrophic runaway outburst flood. Okay, so now let's look at this data from Mars again, but plot a family of curves, that is to say, a family of models that might allow you to interpret something about how those crater overtopping dams are represented in the record. And so we can see here is that I'm showing you a variety of our lowest sloping dams. So these are the lowest aspect ratio. So the sharpest and pointiest dams. And you can see that 3 of the points align pretty well with what our simple model predictions might suggest, except for this one. So this one down here is both sharp and pointy. So it's very tall and very narrow, but the final slope, that is to say, this current day, modern day slope of its canyon leaving the crater is quite low. And so it's about 6 times shallower in slope than you would predict based on our very simple modeling approach from before. And what we might think that that means is that perhaps that flow continued to be sustained in this particular crater for some period of time after the initial outburst flood that may have created the canyon in the first place. So I'm going to plot up all the rest of the data, again, with their associated family of relative curves. And for each of these curves, again, this is a set of model runs with different initial conditions. And then the product is plotted of their final slope. And so you can see that aspect ratio as the color of the line systematically varies as we change those models. And so again, like we keep adding curves here, and you see that once you get to really, really low aspect ratio dams, it seems that it's almost impossible to generate a runaway outburst flood with positive feedbacks. And so this example here, this dam that I'm highlighting, it's interesting because it's really low sloping in both its canyon and on its rim. And yet it is still shallower in slope than you would predict based on the associated model, implying that there might have been sustained discharge and sustained precipitation on the surface. Okay, So I promised experiments, and we're getting close to time here, so I'll move quickly. But we decided to validate and test this experimental frame or this numerical theoretical framework with an experimental result. And so what I'm showing you here is a black and white photo from St. Anthony Falls Laboratory at the University of Minnesota. And so what you can, I'll just sort of highlight a couple things to, because experimental designs tend to be kind of busy and the rooms are messy. So what I'm highlighting here is that we used an 11-meter long flume. So this is quite a long, but also narrow flume. It's only about 6 inches wide. Um, and what we did was we took that flume and then we inserted a canyon a priori. So we basically forced or enforced the canyon, the outburst flood canyon, to be very narrow relative to the width. So we fixed the width of the canyon so as to not so as to reduce the dimensionality of the experiment and enforce a one-dimensional result. Okay. And then we put in a canyon in the middle, and then we filled it up with sand, and then we shaped that sand into whatever initial condition we wanted. So either a broad, low-sloping dam or a sharp, pointy dam. We then filled the upstream portion, so that upstream portion is over there. We filled that upstream portion with water, so as to form an analog or one-dimensional analog of a crater lake. And then we filled it up until the crater rim started to erode. And then we shut the water off at that moment and allowed the outburst flood to proceed. We then recorded the topography of that sand wedge, that dam, before and after the experiments with a measurement cart that moved up and down the length of the flume. Okay, so I asserted to you before that the final slope of a outburst crater depends on both the aspect ratio and the size ratio between the lake and the dam. So here I'm showing you some of our experimental results. So this is the topography, the initial topography of the experiment before and after. And so on the top panel, I'm showing you the initial topography. On the bottom panel, I will show you the final topography. Z on the x-axis, or on the x-axis is x distance, so distance along the flume from upstream on the left to downstream on the right. And then the z distance, or the elevation, is shown on the y-axis from 0 being the bed of the flume, which does not have a slope, to about 35 meters, not millimeters. So I'll clarify that is actually in meters. So they're about, it's about 35 centimeters deep, not 0.35 millimeters, which would be amazing. Really small. Okay. So after the outburst flood, this initial first outburst flood we showed here, again, we have a low, broad slope dam. And then we allowed the overtopping flood to proceed, and negative feedbacks went out. And it turns out that the slope doesn't change very much at all. So we're kind of sitting in this regime right here, where we have a relatively small lake relative to the size of the dam. And because it's so low sloping initially, it does not instigate an overtopping runaway process. Contrast this with with our second event that I'm going to show you here, where we built a sharp, tall, peaked dam. And then after that, positive feedbacks won out, and we produced an overtopping runaway flood, which then leads us out into sort of this part of the parameter space where we have a high aspect ratio or low aspect ratio dam, sharp and pointy, that experiences positive feedbacks and ends up with a slope that scales with the outburst flood. Okay, so then we have another example here where we reduced the aspect ratio slightly, and we still experienced a runaway overtopping flood. And then in this example, we tried to produce an even higher aspect ratio, a lower, broader dam, and produced again negative feedbacks predominated and self-arrested this flood from continuing. And so we're kind of bouncing around either side. All these examples are showing that we're bouncing around on either side of the cusp of that trade-off between positive feedbacks and negative feedbacks. Our last case that I'll show you here is a dam experiment where we created low aspect ratio, wide and broad dam, but because it was so much taller, we increased the size of the lake, and the result was that this one, uh, in this case, positive feedbacks went out, and we end up with a low sloping result. Okay, so those are what the experimental results look like in profile, but now I'm showing you again those data from Mars here plotted up on the graph, along with the associated model curves. And now I'm going to layer on our experimental results. So what we were able to sort of produce here is that several of these several of our experimental results plot generally in the part of the parameter space where we would expect them to. So for example, this curve here was our example where positive feedbacks or negative feedbacks won out. And so we are experiencing a lower slope than you would expect just by initial conditions. In contrast with this one, where the slope remains high because those negative feedbacks went out. So we're sort of on either side of the boundary between those two different processes here. And our experiment, so we're still working on making more of these experiments to continue to explore this parameter space. But what we're finding is that it turns out that it's hard to produce those runaway feedbacks, and it's hard to produce canyons whose slope scales um, with the size of the outburst lake, simply because we can't produce lakes and dams that vary as widely in size as they do on Mars. So we're working on doing that for experimental results in the future. Okay, so I'll just wrap up really quickly here and say that the main control on outburst canyon morphology on Mars is the size of those open basin lakes relative to the size of their dams. But that we found additionally that the aspect ratio of the initial dam, likely controls both the size and the impact of those outburst floods that escape from the craters. And so we're going to work continuing on doing future experiments to separate that erosion component by initial flooding from erosion that may have occurred by prolonged fluvial activity, that is to say, continued precipitation. So this may become in the future a useful tool for continuing to validate not only how much, not only like was there water available to move sediment on Mars, but how much and for what period of time may it have been sustained. Okay, so with that, I'm happy to take any questions, and I'd be thrilled to hear your thoughts.
All right, it's a fantastic talk. So if you, so if you have any questions, just please post it in the chat or just raise your hand, and you can ask Eric directly. Yeah, maybe so before any question comes out, I have a question for Eric. So this is very cool, but I have one question about the lithology. As I understand, so the stream power is determined by the discharge and slope. But I think the erodibility of the lithology as a rim of the dam is also very important. So how do you consider this factor?
Yeah, hard. Yeah, it's a great question. The general way we've approached this is that establishing grain size on other planets is hard. Establishing the lithology, especially on these sort of big sort of global studies, is really hard. The basic one of the foundational simplifying assumptions we've had to make is that, and there's not terrible evidence for this, but one of the foundational assumptions is that the bedrock is so fractured and so crushed by all of the impacts that have happened that it's effectively non-cohesive granular material. And that's like a big simplifying assumption. It's actually one of our next goals as well, is to actually have to vary the grain size in our experimental setup so that we can ask a little bit closer to that question in some ways. But no, we have not actually approached it as a detachment limited problem, but rather we assume that the substrate works like a non-cohesive granular material. And so we apply a sediment transport relationship for that context, not for a bedrock context. So I totally agree. I would love to know. We are unfortunately forced to impose this kind of simplifying assumption. So that's what we ended up doing. But we can explore, the best part about models and experiments is you can explore so many different parts of these processes in the lab. So
Yeah.
Okay, you have a question in the chat. That's what we'll do.
oh,
We'll
let me
just
pull it
read it
up.
for you, but please feel free to read along as well. So the first question is, how did you control, sort of, I guess it relates to the ages of the craters. So how did you control that? You've been studying crater rims on Mars with the same age and hence the same state of erosion. So perhaps maybe talk a little bit more about timescales of the processes you're looking at. Thanks.
Yeah, yeah, it's a great question. Uh, they're all about the same age. However, they do vary in their. I'd have to go back. My time scales are better on Earth than they are on Mars, and so I'd have to go and check Tim's paper just to make sure I know exactly what ages they all are thought to be. Um, but they're all comparable in age, but they are not all comparable in their state of what you would call degradation. So some of the crater rims have certainly degraded more than others for a lot of different possible reasons. So yeah, there's a little bit of degradation that happens there, and so we're doing the sort of the best we can. Um, but yeah, I agree the amount of degradation you expect from subsequent erosion of various kinds is certainly a big problem that one could have. And I'm not sure exactly how to solve it other than to control for age, but they're all about the same age, but there's also all kinds of stuff happening spatially on Mars that's different as well. So um, I don't think that age would necessarily fix the problem if we were able to all stick to a single age category. But I suspect that if we sort of classify them according to their state of degradation, we might find a similar trend as well. And so we haven't done that because it turns out that aspect ratio seems to be a pretty strong control, um, even when we haven't controlled for it. But we could put a finer point on it for sure.
Yeah. So we have a second question from Anne. So she asked, are you planning on doing a similar morphometric analysis on human-made dam outbreaks on Earth? Would you expect similar results given different dam size, material, and gravitation acceleration? Yeah, very cool question. Yeah.
Yeah, it's a great question. Most of the sort of human-made dams have extremely small aspect ratios, that is, they are very sharp and pointy. And so almost all of them lie in that domain of catastrophic outburst. Um, so yeah, it's a great question. Based on our really simple framework, almost no dam is basically insensitive to overtopping. Um, but it is interesting to consider how you could change the material properties and consider it. So I do love this question because the material and gravitational acceleration are super important components in the model. Um, and we would know a little bit more about, for example, which ones might be safer. But I think the sort of, if we were to make an engineering recommendation from this, which I certainly would not dare to in writing, but one might suspect that if you made dams that are really long and broad, they would be certainly safer from overtopping. But I think it would be hard to make the economic case for that. But yeah, it's certainly something I've considered. But another interesting case, though, and that I am thinking about is glacial outburst floods. So there are a lot of glacier-formed moraines, especially in the Himalayas, as they start to melt, where these kinds of outburst floods may be really impactful. And so understanding how those moraine dams and ice dams form is also quite relevant. Yeah, and the ice dams have the entirely different material properties. So yeah, it's a huge parameter space to explore. Oh yes, so I'll answer
Great. Yeah.
Kai's.
So if I just
Um,
quickly if I can just read out the question just for those
Yeah.
people that can't see the chat, is that
Oh,
okay?
sure, for sure, of course.
So there's a question here just about the duration of your model and your sort of physical and numerical model experiments.
Yeah, they're quite short. So uh, the flume experiments take on the order of a few minutes from start to finish, like once the rim starts to overtop. Um, and because so yes, they're quite short, on the orders of seconds to minutes. And I've tried to scale our experiments to the numerical results because that was the main motivation for them. So they're quite short. If we increase the scale accordingly, the time of the flood actually also increases. So this is one of those rare experimental results where scaling is actually kind of feasible. So a lot of the time when one is trying to do sedimentary experiments of any kind, the Reynolds numbers and fruit numbers just cannot match the natural system that you wish to model on an appropriate scale. So as you reduce the amount of time and the space, uh, the the material properties of the sediment and water you're using fail to reproduce the correct Reynolds numbers mostly. But in this case, because it is such a fruit number, like such a critical flow dominated process, it turns out that this one we can match the fruit numbers relatively well, and we don't have to match the Reynolds numbers relatively well because the inertia and the momentum is such a much more important component of the flow than is the viscosity. So in this case, it turns out that the timing scaling actually might work pretty well, really, in a way that it wouldn't work in some other contexts. That's more
Right.
than you asked, but it's the idea.
Yeah. Okay. All right. We have a question from Trevor. He asks, if you have modeled the same problem for the failure of ice dam lakes on Earth.
No is the simple answer, and no is the simple answer, and I would love to is the longer answer. Um, yeah, we have not done so. This is such a simple model. This is not also, I'm not the only person who has attempted to do this, and our model is so simple intentionally to capture a broad trend in something where we don't have a lot of um, uh, on the ground validation of the components and the material properties. So again, on Mars, we just don't know much. And so a simpler model to capture the basic interplay between positive and negative feedbacks in the system is important. And so we've neglected intentionally a lot of the important complexity that you might want to capture if you were wanting to extend this to another environment and tell about the differences between, or may even make more concrete predictions. So that's our motivation and the reason why we haven't done a more complex and powerful modeling approach. But that is not to say that that is not being done. So there are groups all over the world who are interested in dam overtopping from an engineering perspective, as well as from a scientific perspective. And so I do believe there is, I can't off the top of my head remember exactly where I would find which paper it is, but and who the author is, but there's a very cool paper that discusses a quite a detailed one-dimensional physical model of how a dam of some kind might overtop an outburst. And so one also wants to know things like the internal angle of friction of the material, whether it fails catastrophically in a landslide, and all these kinds of things are important, and especially when it comes to ice dams. Um, and so yes, this is to say, I think that is certainly being done. We didn't do it here, but one could easily extend this modeling framework in the same way.
Yeah, okay. So I have one more question for Eric if nobody is asking for now. So as I'm thinking, well, I mean for the small lakes, because as I remember you said in the flume experiments, you stop your input of the water once the outburst happens. But what happens if in the small lakes the ongoing precipitation is keeping rising the lake level here you have discharge, you have, more water coming into, I think maybe the positive feedback is even stronger. Then they have another competition, maybe acceleration of the positive feedback.
Exactly. Yeah. I didn't show those results. So we did actually do this.
Oh, really?
Yeah. Um, sort of. We kind of did it. The what you're describing is like what if the system is open and you continue to put water in? And because we were interested, so we kind of restricted ourselves eventually to the minimum case. So what's the like minimum amount of water and what would form a canyon and what would the shape of that canyon be if the only process was overtopping because it just got to the threshold.
Yeah.
Um, and so that's what I focused on here. But in a couple of experiments, out of pure frustration or a fit of pique, one of a few times I actually did just keep running water over it. And I just kept, basically we had a hose. And so I just kept the hose on, and continued to push water through the system for a long period of time. And what happens is it slows down, but you do ongoing continued fluvial activity when you have no supply of sediment upstream just continues to lower the slope of the river. And I think this is not unexpected. It's pretty obvious as an outcome. But it just goes to show that if you continued to have sustained fluvial activity, the outcome would be that the slope would keep dropping as because there's no input of new sediment at the crest. And so you have to basically continue eroding down the canyon. Yeah, and so another problem that one might have eventually as well in this case is that uh, it turns out that the crust of Mars probably gets more lithologically like rock the deeper you go. And so, yeah, you do have an important problem where the lithology and the erodibility of that lithology probably changes with depth as well. So, um, lots of complicating factors on Mars. I can
Okay,
read the next question too.
we have another question in the chat from John saying, do you study or consider or think about the different gravity, basically, and how different gravity on Mars would change the capability of the water to erode the land surface within the channel? Sorry, within the channel.
Yeah, it's a great question. The way I formulated this model, because it is so simple and depends on very simple, it's a very simple geometric model. It doesn't have a spatial component whatsoever. Um, the framework we used is actually ends up being non-dimensional. So gravity cancels out in our formulation here. So in this case, it is kind of agnostic to the gravitational field that the system is sitting in, because the only thing that's important is is the specific weight of the sediment sizes. So we ended up formulating it in such a way that gravity is irrelevant in this particular model, again, because it is so simple. Um, However, if you were to move to a different framework, like especially so one of the most common ways I've seen this modeled before as well for really big floods is as a block toppling model. So you can imagine if you have even fractured basalt or a variety of different things, you can imagine the major process that allows erosion at the crest of the dam, or along the slope of the bottom, as well as to pluck blocks off the bottom and force them to fall over. And so that would be a totally different erosional process. And if you wrote the model in a different way, gravity would not cancel out in the same way that it does in the way that I formulated it. But I did specifically to avoid this question.
Oh, yeah. Great question. Maybe if we have time, maybe just quick answer. Is the density of the water a matter? Because I've heard on Mars it's simply more brine than fresh water.
Wow, that's awesome. No, definitely did not vary the density, but if you did, then you would want to scale it accordingly. I'd hope that it would be the same for all the craters.
Yeah.
And I'd hope that it would be but then comparing our experimental results probably is non-trivial as well in this case. But yeah, it's a great question. That's so fun. I would love to use a brine and then also a freshwater in the same experiment. Let's do it.
Yeah. Okay. Great. I didn't see any further questions in the chat, and also we are close to 1 hour. If it's
Yeah, I don't want to
okay
take
for,
everyone's time.
yeah, we are just on time. Oh, there's another question. Let's see. Okay, maybe Eric, so you can read it by yourself.
Yeah, I'll read it out. So what Peter and John also say, I think they must be sharing. What Peter says is, yeah, the density of water is strongly affected by atmospheric pressure. Hence, by the time when the water is flowing over the surface, once the pressure is too low, there's boiling and large amounts of bubbles. Yeah, um, cavitation and boiling as a result of a drop in atmospheric pressure could be could be an important process. You know, it's interesting. Um, I think we don't have a good grasp at this particular time in Mars's history what the atmospheric pressure was and whether so there's good evidence to suggest that this is not just groundwater welling out of the subsurface, but rather is precipitation at this particular time. And so I suspect my knowledge of this is a little bit limited on the sort of dynamics of how exactly we think Mars's history has changed, but atmospheric pressure probably wasn't a lot lower, or wasn't a lot higher than it is at any particular point in the history, but there was sort of surface water moving around. And so I don't think we have good evidence to suggest that water is boiling on the surface of Mars during this time. Um, in particular because you can see deltaic deposits and similarly aged glaciers, with sedimentary structures that mimic or at least look a lot like the ones we find here on Earth. Um, and so, especially with quite large clasts, so gravels, for example. And so I don't think, based on what I know, again, not being a Mars person per se, but rather a dabbler in our red planet, um, that it's probably not happening at the time. Oh, yeah. So they're Hesperian or Noachian, I think is exactly how old they are in the general frame of things. So what Peter says is uh yeah, but the age of the he asked about the age of the craters because if they were actually very old, so yes, they are very old. They're sort of 3 billion years old. Um, Pressure would be much higher, but if they're young, Amazonian, which is the more recent time in Mars, this might be a funny issue to play with. Yeah, so exactly. No, they're very old. Yeah, they're 3 billion years old, but again, I don't really know Mars timescales that well. It's like such a different environment with such a different timescale than Earth, where we have no fossils and things like that. So I'm so used to an Earth framework. So yeah, thank you. I appreciate the feedback and thoughts. These are great questions.
Yeah, okay. Okay, yes, all right. We have no more questions for now. Yeah, I think so if this is okay for everyone, we are going to end this session. And thank you, Eric, for making this fantastic talk, for getting up so early, and thank you for everyone to attending.
I love
And
it. Thank you for the invitation. It was so much fun.
yeah, we'll see you all in the next session in the next week. Yeah, right.